All right, so we'll talk about first what an exponential function is. We'll talk about how to graph them from a table of values. This is like the long way to graph, and it helps us to understand the way that they work. But eventually I'll show you a quicker way to get them graphed. And then we'll look at some of the important and key parts of exponential functions, like their y-intercepts. We're going to learn of a new thing called a horizontal asymptote today. And all exponential functions are either they're either called a growth or a decay. And so we'll learn how to tell which one is which. So let's begin here. An exponential function is a function that looks like this. So the real part that makes it exponential is this part here. Okay, it's whenever you have a number raised to a variable power. So when the x is in the spot where the exponent would be, that's an exponential function. You could have a number in the front here. Usually you do, but you don't have to. You can even have a number being added or subtracted after that, but I'm going to stay away from that for today. We'll talk about that at another time. But an exponential function is any time you have a number being raised to the power of x of some kind. That's what an exponential function is. So just some important things to notice. Notice that the x is the exponent. The b is called the growth factor, this guy right here. Based on what that value is, that tells you how fast the function grows. If it's a bigger number, then it grows faster. You have a steeper line. If it's smaller, then you have it grows slower, and it's a little bit more flat. But in general, all exponential functions grow pretty quickly. It's also known as a base, by the way. So take a moment and see if you can identify which of the following is not an exponential function. Just look at it and see if you can figure out which one is not. All of them are except for one. We want to take a guess at it? Go ahead. Huh? The third one, good. And how did you recognize that? There's no... There you go. The power is not x here. So since the power is not x, it's a number. That's actually just a polynomial there. This is the one that is not an exponential function. All the other ones have an x in the power spot. So the rest are all exponential functions. All right. All right. So what are exponential functions useful for? They're useful in describing how certain things grow or decrease, which in this case we're going to call it decay instead of decrease over time. Population growth we model that with exponential functions. Populations don't grow linearly. It's not like every year you have this many more people born. They grow faster than that because, let's say that, your parents had 2 children, and then each of those children had 2 children, and each of those children had 2 children. It grows faster and faster and faster. And so it's not going to grow at a steady rate. It's going to grow faster and faster. So population does that. Disease spreading is another one. Interestingly, radiation is another one. So seeing like, you may wonder, what do we care about radiation? But they actually use this to date things. So they'll dig up a rock and they'll say, okay, well, based on how much carbon is in this sample, we can say how old it is. And the amount of carbon in there decreases over time, and it does so exponentially. So you can use exponential functions to look at how quickly certain things grow and decrease, okay, or grow and decay, let's say. All right, we're going to need calculators today. So come and grab a calculator if you want. Just have one person from your table do it, or if everybody wants to get it, it doesn't matter. Just come grab a calculator. Okay, so we'll start by doing it by hand, but then we're just going to use calculators most of today, okay? So I've got a table of values, and this is we're going to graph it. Okay, so I've got some x values I've given you. There's a really weird one up there, -30. You'll see why I put that there in a minute. But we're going to plug these in for x. We're going to get the y values, and for each pair, we can plot it as a point and connect the dots. You could do that with every function. It takes a long time to do it this way. Like I said, I'm going to show you a faster way to graph later. But for today, this is cool because it helps us kind of see some things happen with these functions as we do it. So I'm going to go ahead and start at the bottom here with 3. So if you wanted to do this by hand, you would replace the x value with the number that is in the x column there. So I'm going to plug in 3 for x. Now, in order of operations, what would I do first? The exponent. So I would do this first, 2 to the 3rd power. What is 2 to the 3rd power? 8. 2 times 2 times 2 is 8. And then we do our multiplication next. 3 times 8 is 24. All right. Why don't you guys try doing these 2 boxes real quick by hand? I'll ask you what you got in just a second, and then we'll do the other ones together. Most of them on the calculator. But try these 2 numbers, plugging in 1 for x and 2 for x by hand, and seeing if you can calculate those real quick. So look at the pattern going on here. What do you guys predict that next one's going to be? It's going to be 3. I guess you guys getting halved every time? Okay, but I'll still work it out for you and show you why that one's 3, because it's a little bit weird. The next one we're plugging in 0 for x. Okay? And that's where it gets weird, because when you have something raised to a 0 power, you guys remember what that is? It's 1. Which is, that doesn't really fit in our minds like an obvious thing, but a number raised to the 0 power is 1. So that's how that comes out to be 3. Okay. Now for the rest of these, you don't have to write it. I'll show you how to do it by hand just for fun, but you don't have to write that down. Because we're gonna, for the negative ones, and honestly from here on out, if you just want to use a calculator, you can. But I'll show you one negative one by hand. And like I said, you don't have to write it, because I'm not going to ask you to do this, but at least for today's lesson. But I'll do one by hand. So you ever know what negative exponents do? It makes it a fraction. It flips it over. So this 2 becomes a 1 over 2. Multiplying those together, 3 times 1 is 3, and 3 divided by 2 is 1.5. Okay, so you could do it by hand, but I'm not going to ask you to do that. We're going to do it on a calculator. So why don't you guys follow along with me here. Get your calculators out and ready. Turn them on. I'm grabbing some of these, and mine aren't turning on. Make sure yours aren't turning on, and grab one of these blue ones. Okay, well, here's how we do it. On your calculator, if I wanted to figure out what this was, 3 times 2 to the negative 1. First of all, go ahead and type 3 on your calculator. So go ahead and push 3. We could do parentheses. You really don't have to, but we could do parentheses. The parentheses are located right here. Right above the 8 and the 9. So put the 2 in parentheses. Now, the way you get the power on there, guys, is with this button here. It looks like a little arrow pointing upward. It's called a caret. So if you push that, on these ones, it will actually make it look like an exponent, like the numbers will get smaller and go on the top right-hand corner. If you have one of the regular blue calculators, it'll just put that symbol there, but it means it's power. So if you have a blue calculator, it's just going to do that. And then we're going to put negative 1. But now let's go ahead and do negative 1. Now, Remember, when you're doing negatives, you got to remember there's a difference between the negative button and the minus button. We want -1. This is the negative button down here, so -1. And even though it's not written this way up there, and honestly, it probably will work anyway, for other things we're going to do later, it's good to get in the habit of just putting this in parentheses, even though it doesn't have parentheses up here. I would put your exponent in parentheses. It's just a good habit to get into. So use your caret button, put -1 in parentheses, and push equals. And we should be getting the 1.5 that I showed you we got earlier, right? All right. So let's do another one. Let's do -2. Let's see what you guys get by doing -2. Try that, and I'll ask you what you got in just a second. So that's what they look like. They have a flat line here that they can't reach, and that's called the asymptote. But that's what their shape looks like. Whenever the graph gets bigger in this direction, it goes upwards in that direction. That's what we call a growth function. Okay? So horizontal asymptote is an invisible line. It's a y value that our function approaches, but it never reaches. On the last one, what y value was it not able to reach, but it was trying to reach it? 0. So y equals 0 would be my horizontal asymptote. So here's one for you guys. Just use your calculators to complete this and see if you guys can sketch the graph. It'll look a lot like the one that I had, but it'll have a couple things that I'd want to point out. But go ahead and do that one real quick. So Lily, I'm going to have you help me fill these numbers in here. What did you get here? Uh-huh. Uh-huh. And that just means it's a really small number. It's basically just going to be 0, same thing as last time. Anybody have disagreements on these numbers here? Are we happy? All right. So I'm going to graph it. Now, the one I really want you guys to pay attention to here, this one I'll just throw out there as a volunteer question. What's the y-intercept on this thing? Where does it touch the y-axis? It touches it at 4, right? Now let me erase this. What was the y-intercept on this one that I did before? 3. Can you guys see that number right there? All right. Over here, your guys' y-intercept was 4. That number right there. Why is it this number here? Well, because when you plug in 0, which is what you do to get your y-intercept, when you plug in 0, that 1.5 just basically goes away. It becomes a 1, and you multiply it by 4. And that. So this here, you might want to label that. That's our y-intercept. Okay. So 1, 2, 3, 4. I'll put a dot here. We see that at -30, it's basically y equals what? It's about 0, pretty much 0. It's really low down there. At 3, it's 13.5, so I'm going to go over 3. So at 3, it's about 13.5, which is up here. Now, you guys probably plotted all the rest. That's fine. But those other points are kind of not super important. I know that on the left side, it's basically 0. I know that it's touching the y-axis here at 0, 4. And I know the last point's somewhere way up here. So I know the shape is basically going to look something like that. Okay? So we're kind of getting close to the side of going a little bit quicker. We really only need to know the y-intercept, where it's 0, and where it's going up. Now, we'll find something interesting happening here with our next one that we do, though. Where was I? There it is. I was on this side the whole time, and I didn't realize it. I was doing the last slide. So here's another one. I'll give you guys a couple minutes for this one. Now this one will turn out different though. So see if you guys can see what's different about this one. Go ahead and work that out. I'm going to skip the other numbers because we don't really need them. But here's what I know. Let's go ahead and graph it. I'm going to go over 3 to the left and the right. I see that at 3, it's 0.375, so that's going to be really low, right down here like that, right? So at 3, it's 0.0375, really close to the x-axis. I see that at 0, we have a y-intercept of 3. I didn't do negative 3. I know that negative 30 is going to be somewhere over here, and I see that the y value is astronomically huge. In other words, it's somewhere up here, right? Way, way up there. So my graph is going like that this time. You guys see how that graph is backwards? It's going in a different direction. What do you guys think about this function is different that causes it to go this way instead of this way, which the other one did? Does anybody? What's less than 1? The b value, the base. When this number here is less than 1, as we move to the left, it goes down. It's decreasing. If this number is bigger than 1, then as we go to the right, it goes upwards, and that's increasing. So that's what we call growth versus decay. All right? All right, so here we go. Growth. If the growth factor, if you don't remember what that is, I'll remind you. That's the b value. If the growth factor is greater than 1, then the function increases from left to right. So draw a picture like that there. If the growth factor is less than 1, like 0.5, then it decreases from left to right like that. Technically, there's an arrow on the other side, but I like to think of direction moving to the right, because that's typically how we think of math, is moving to the right. Okay. All right, so we know what an exponential function is. Looks like this. We know what they look like. They look like this. If they look like the top one, it's called a growth. If they look like this, they're called a decay. We also learned how you could tell where the y-intercept is. It's just this number, right? Okay, so we've got enough information to move on to our last bit for the day. Here it is. So example 2. I'll do this one. I'll let you guys do student practice too, and we'll see what happens. So for the following exponential function, identify each item specified. What would the y-intercept be? Shout it out. 3. It's that number right there. So I'll just circle it and put it here. That's where it will touch the y-axis. Now, the real way to find a y-intercept is plug 0 in for x, but that's just going to cause the 1.25 to go away, and we'll just be left with 3. All right, horizontal asymptote. All day today, what's been the horizontal asymptote? What y value is it trying to approach? 0. Now, it won't always be 0, but for today it will be. So in other words, my function is trying to get down to that x-axis where y equals 0. It'll never reach it, but it tries to get there. Growth factor and base. What's the growth factor and base? Well, that's this number right here. You might want to just circle that and draw a line here. The growth factor, or base as it's also known, is 1.25. Now, is this exponential growth or decay? Why is it growth? Because my b value, what's my b value? Well, what's the number for it? 1.25. Is 1.25 greater than 1 or less than 1? So since b, which is 1.25, is greater than, oh, I put 0. I messed up, sorry. It's supposed to be 1. So if this is exponential growth, since b, which is 1.25, is greater than 1. If my b value is less than 1, that would be a decay. So I know that this function, if I graphed it, would look something like this. But we'll get to that on another day. You don't have to worry about graphing for now. Okay, so you should be able to identify your y-intercept. horizontal asymptote, growth factor, and tell me whether it's a growth or a decay at this point. Any questions about any of that stuff before we roll on? So there's a student practice for you. And I think that'll be it for today. So go ahead and try those things, and we'll see what you guys get.